Hey, Gregory Carlson here with the Calculus Building. We just learned how to find the difference quotient of a function. So now let's do the difference quotient of a few applications. So the first one is about utility. And I have a degree in economics. And utility is when you buy a product, it's the amount of happiness you get, the net happiness you get for buying that product. So that's what that means. Utility is a type of function that occurs in economics. When a consumer receives X units of a certain product, a certain amount of pleasure or happiness or whatever is derived. Here's the graph of the utility function, and they want to find the average rate of change of utility. So how much more happiness are you getting from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So this will be pretty easy. I'll just show you how to do one or two of these, and I think you'll get the idea. So as you know, the rate of change formula is similar to the difference quotient. It's basically the slope formula. It's y2 minus y1 over x2 minus x1. And remember, this is another way of saying y2 and y1, f of x2, f of x1. So let's do it from 0 to 1. I'll just look at my graph. Here's my second point, 170, and my first point will be the origin, 0, 0. So I do y minus y, which is 70 minus 0, divided by x minus x, which is 1 minus 0. Which is easy. 70 minus 0 is 70. 1 minus 0 is 1. So the average rate of change from 0 to 1 is just going to be 70. Now remember, that's the slope of the line from this point to that point on the red dotted line. Let's do one more. Let me do 2 to 3, and then I think you'll be able to do the rest. So the average rate of change from 2 to 3, I would look at those 2 points. And once again, I would do y minus y, so that would be 140 minus 110 divided by 3 minus 2. And again, that's pretty easy to calculate. That'll just be 30 over 1. So the average rate of change is 30. So you'll notice that that's a little bit smaller than our change from 0 to 1, and that makes sense because it looks like it's a little bit flatter here and is a little more steeper here. And in fact, with utility functions, the way it works is you get some happiness out of buying your first hot dog, say, and you get happiness out of your second hot dog, but not as much as the first one. And every time you buy another hot dog, you know, the additional happiness you're going to get is going to get smaller and smaller and smaller until eventually, like if you ate 20 hot dogs, your utility function might even decrease after a certain point. So this is the marginal rate of change of utility. And remember, these are pretty rough approximations of the instantaneous change at these points. Remember, this red dashed line you see here, we were finding the slope on the red dashed line. That's what we were doing, of the points between the rise over run of these. And so as soon as we get to the derivative, we're going to be able to find the instantaneous rate of change of those things. Let's look at the next example. It says, suppose that a fashion, and I know this is difficult to read, but hopefully you can read it on your paper. It says, suppose that a fashion company determines that the cost in dollars of producing X cell phone sunglasses is given by this cost curve right here, which is negative 0.05x squared plus 60x. Calculate this difference quotient from 351 to 350 and determine the significance of it. So let's go ahead and do that. Let me scratch out the answer so you can't read it. So we want to find C of 351. So, I mean, to calculate this difference quotient, on the bottom we have 351 minus 350. So that's pretty basic, just those numbers there. Now let's calculate C of 351 by plugging 351 in for x into the function. So that'll be 351 squared times 0.05. And that is equal to, oh, and we'll slap on a negative sign. Well, I'll slap on a negative sign, so that's because of the negative sign there. So that's negative 6160.05. And then that'll be 60. Hang on, let me clear the calculator. 60 times 351 is 21060. So that's just me plugging 351 into the equation. So let's do 21060 minus 6160.05. And we get 14889, I'm sorry, 14899.95. So again, that number I just calculated right there is calculating C of 351 and just plugging in 351 into the function. So that's going to be minus C of 350. So if it's okay, I'm just going to scratch this out. And let's calculate it again for 350. So I'll clear the calculator. 350 squared times 0.05 equals, and we slap on a negative, we get negative 6125 here, and 60 times 350 is equal to 21,000. So adding a negative is the same as subtracting, so we'll take off 6125, which gives us 14875. So now we're ready to calculate this. So on the bottom, I have 351 minus 350, which just equals 1. And on the top, I have 14899.95 minus 14875, which gives me an answer, and that's just a little floating point error. If you want to take one of my cryptology classes, I guess it's not cryptology, but when you get into computer programming, you understand a little bit why those errors, rounding errors, happen. It's because the computer is in base 2, and sometimes there's little rounding errors when you go from base 10 to base 2. But anyway, the answer is 224.95. So there's your average rate of change. And so this is important, which of these does it represent? Is it the cost to produce, the average cost to produce 351 items? No, that's this number right here. Is it the average cost to produce 350 items? No, again, that's this number right here. Remember, when we're doing an average rate of change, we're looking at the marginal change of something. Is it the average cost to produce one item? Definitely not. It is this one. The average cost to produce one more item after making 350 items. And so that's really important. When we're doing these average rate of change or the derivative, remember we're looking at the rate of change of something, or the marginal change, the change to make one more item after the one we've currently made. So that's the answer to that question. Let's do this last one really fast. An object dropped from rest from the top of a tall building on planet X falls a distance of d of t equals 18t squared. So there's the distance function, and that says feet in the first t seconds. Find the average rate of change with respect to time as t changes from t1 equals 4 to t2 equals 7. So once again, this is just a average rate of change problem. And so it'll be d of t2 minus d of t1 divided by t2 minus t1. And remember, this is kind of like y minus y over x minus x, except this time x is t and y is d of t. And this is pretty easy to calculate. So on the bottom, we'll have 7 minus 4. And on the top, we just plug 7 and 4 into the function. So d of 7 is going to equal, let's clear the calculator, 7 squared is 49 times 18 is equal to 882. And now let's plug in d of t1. We'll plug in 4. 4 times 4 is 16 times 18 is 288. So on the bottom we get 3, which is 7 minus 4. And on the top we have 882 minus 288, which equals 594. And then we'll do 594 divided by 3 to get a final answer, which is 198. Now, what are the units on this? They tell us that it's average velocity. And so when we do this average rate of change formula, this average rate of speed formula, remember, you're going to get a rate because we're looking at your average speed. So this is going to be feet per second. So the average rate of speed when you're going between 4 and 7 feet of an object that's falling on planet X is 198 feet per second. I hope all of those examples make sense. They're not too difficult, I hope. And remember, what we're trying to build up to is taking the limit of this as x2 approaches x1. Once we add that piece, we are actually going to have the derivative and the instantaneous rate of change wherever we want, which is way better than these approximations. So I hope you're excited, and I'll see you in the next video. If this was helpful, please like and subscribe, and thank you so much. See you next.